Check, check. Okay. Okay. So I was trying to do my research, and I got sidetracked looking at this paper, which is really cool. And I'm going to read it to you. Applications depend on persistent storage to recover state after crashes, but the POSIX interface does not define the possible outcomes of a crash. And if POSIX doesn't define it, that means it's different when you have ext2 versus ext4. And that means Git or something that uses your file system has to care. It's not supposed to care what file system you have because there's this POSIX interface. But if something's not defined by the POSIX interface, it means it ends up caring. Like the behavior of it has to take that into account if it wants to be correct. As a result, it is difficult, understatement, for application writers to correctly understand the ordering. And this paper presents crash consistency models that describe yada, yada, the formal something or other. Okay, introduction. Many applications interact with a file system and use them as persistent storage. But if you mess it up, you get data loss. So this is an example that they're saying. This is called, it's bad when the bug has a name, the 2009, and the name's got the year, the 2009 ext4 data loss incident, which multiple users reported that pretty much any file written to by any application became empty after a crash. I was like, oh, what kind of paper was that from? So I clicked into the link, and it's a bug report on Ubuntu. So that's awesome. So what is this ext4 data loss incident of 2009? So the root cause is the pattern in figure 1A. Okay. FD equals open, and then we write something to it, and then we close it, and then we rename it. And that's supposed to be, why didn't you just write it to file in the first place? Why didn't you do file.temp?
Something's looking at file.
Yeah, you want it to be atomic. You want whoever is looking at file to either see the old one or the new one.
Right. They don't want to see partial right.
They don't want to see the partial right.
Does this have something to do with the copy versus move stuff?
I think that maybe not.
Okay.
Is it because they missed an fsync? Or msync, I forgot.
Well, they should probably have an fsync before the close. That would indeed fix the bug, but it's also because they don't understand, it's unspecified. That's the bigger problem, because there's conceivably a file system where that would work fine. But POSIX is not specified, so it means it depends on your file system. The root cause, and they're going to tell us the root cause, so let's see what they say, is that it's intended to atomically update file, but due to modern file system optimizations, the effects of the program do not necessarily reach the disk in the order that they are executed. Only the orderings in figure 1B are enforced. So what the hell does that mean? So that means that we know for sure the write happens after the open, and this write happens, I don't know, I was confused why there are two writes. I think this one should be a close, because I only see one write over here. And then we know that the rename has to happen after the open, but relative to these two, they're unordered. So the write and the rename can happen in any order. If there's a crash. If there's not a crash, it seems like it is correct and it's atomic, and it either old or new, and the rename happens after the write. But if there's a crash, it seems like that is where you can get this oh, we don't know which happens.
If there's a crash, why would all of these necessarily happen at all?
Because of journaling file systems, it got part of the way there, and then it crashed.
And then it knows that it has ending operations to do or something?
That's what you ever booted up your system and it's repairing the journal?
So the close and write have happened before, but rename doesn't?
Yeah, wait, what did you say? What is that word?
That happened before
Where did you learn that?
from the college book.
Yeah. So happens before is you maybe, and they were probably talking about memory consistency. And what this paper makes a big deal of is they're bringing memory consistency. They said it in the abstract, I kind of glossed over it, but they're using the memory consistency language and logic to describe file system consistency. Happens before is what it sounds like. It's a partial order.
I think I heard about this term in distributed systems.
Yeah, that would be the other place. That would be Lamport vector clocks.
Oh yeah, exactly.
Yeah. I mean, some keyword, it'll be deep in your gray matter, but some keyword will kind of activate it. And for me, vector clock, if you've ever taken a distributed systems class, they're saying that if you consider a clock to be a triple of all three of these counters, sometimes one of them will be completely before the other one. sometimes like the other one will be completely before the former, but sometimes they'll be independent, which is where you don't really know which one happened first. So happens before is something called a partial order, which means sometimes the events are not like, sometimes you know which one happens first, but sometimes you don't. Sometimes it's neither. They're like independent of each other. Yeah.
What does like set partial ordering have to do with like why are those two things the same?
Well,
Like what is the set?
happens before is a binary relation. It takes two. The binary relation is like a function. It takes two events, A and B, and we say they're in happens before, like A, and I'll write that like A happens before B, if and only if they're in this relation. And this relation is transitive, symmetric, reflexive, and that's the definition of a partial order. So it happens before is a partial order. Because if A happens before B, like, and then B happens before C, let's say, then we can know the open will happen before the close. Because open happens before right and right happens before close. So it's transitive and it models a partial order.
Kind of be relevant, but why is it called partial?
Because a total order would be like, it's like a list and you instead of a DAG, and you always know which one happened first. But a partial order is like a DAG, and sometimes you don't know which one happens first. They're like here.
Like what happens before right or what happens before right or rename? We don't know.
Yeah, we don't know. I mean, neither one happens before the other for sure. So neither. It could be, or the rename could happen first.
Yeah.
So in the official happens before, when you're saying in English versus math, in math happens before, you'd say neither happens before the other. But in obviously, well, yeah, okay. So that's what we're going to model it as. And then this paper had some more bangers, like
I think I missed something. Why is it not just a linear like structure in this case from the code? Why doesn't the code just create a linear diagram? I guess single.
because of file systems, now modern file systems use buffers and they reorder your stuff. And so you don't really know the order that it's actually going to happen in. So even though the code is written in order, the events that the code triggers get reordered in buffers, and the metadata gets like happens at a different time than the data.
It seems like there has to be some guarantee for anything to work at all. Then how can it just arbitrarily reorder stuff without breaking everything?
Well, the memory consistency model, it's unspecified, but it does have some rules. One of them is that if you do a close and then an open on the same file, you should get what the previous guy wrote, right? So there are some rules that make it such that you can program, but there are not enough when there's a crash. And it's possible that ext4 has very specifically defined behaviors, but they're just not part of POSIX standard. And they might be different than what ext2 offers. Does that make sense?
Kind of. Yeah. Sure.
So basically, the issue is that it's not clearly defined that rename should come after close.
Yeah. Yeah. If there's a close and a rename, it's not defined that and in fact, file systems will take advantage of that too when they're doing optimizations. Rushin?
I forgot to ask, what do you mean by a crash in this case? Is it a full system crash?
Yeah, it should be a full system crash.
Okay.
So including a
application's
kernel
going
failure.
down and coming back up, and you expect expectations about the state based on the order of the program.
Yeah.
and then those are not that.
Yeah, exactly. And who is to blame on that is like my favorite question. So on the one hand, writers argue that file systems are broken and too aggressive about buffering and reordering file operations. On the other hand, file system developers argue that this behavior is allowed by POSIX with relaxed memory ordering is necessary for performance. So for the file system developers, so ButterFS developers trade off between performance, which does a lot of reordering, and not being performant, having no reordering, but it's predictable.
But I mean, when you're like entire system crashes, you don't really restart and resume where you left off because you don't know
Yeah.
where it crashed, bro.
Yeah, but the 2009 file data loss event, any file written to by any application became empty after a system crash.
Wait, what do you like? You have to fix it? Or like if the crash happened while the writing was happening?
I think they're talking about the files that were accessed while in this manner.
But then when does the crash happen? Afterward?
The crash happens sometime in here. You don't know.
Okay.
It just
but, like,
happens sometime.
before the rename happened.
No,
Yeah.
I think it happens after, but it's still in the journal and hasn't been written to your disk.
Yeah, and some people would say then the rename hasn't really happened.
I mean, I think the file system should do something periodic in the background, right?
Yeah,
It's probably
every
not-
5 seconds or something.
It hasn't happened when your file, what that
Yeah,
crashed.
and so, and you could also just put fsync before the close. Okay, but here's the problem. Different, in practice, I just talked about the file system developers. Now let's talk about the application developers. Application writers make assumptions about crash guarantees base their applications on these assumptions. Being too optimistic about crash guarantees leads to data losses. Oh, snap. But being too conservative leads to unnecessary synchronization, costing energy, performance, and hardware lifespan. It is thus critical to describe, and then I thought they had some bugs. Oh, so I think these are bugs that they're talking about. So 10, 49, 62. Oh no, that's a paper. Yeah, so that's an actual just bug that's filed. So I like that they had real world kind of things. Yeah, a little bit. Yeah, these are like citing like mailing lists, like the and the SQLite website and stuff, which is pretty cool. So they propose crash consistency, and they basically define mathematically what reorderings are permitted. And then they test it, and then they also like you can give them like an application or like a litmus test, so it's like a sub part of your application, and they'll like try every possible failure thing that's allowed, every allowed trace by the specific consistency model, which is kind of interesting. Do you want to hear more about the consistency model or more about the litmus tests?
I think I read a similar paper. It's not this one.
The model.
Okay. So I'm going to pass up the tests, which were right here. This is an example of a test. And this is the example of the observed. We found an execution which unintuitive behavior. This is an example of when they think that the test will be confusing. For the model, they define basically, I think that this paragraph is the important one. So assume the program is written and the program does write, and fsync, and they've just labeled them E0, E1, and E2, where E0 is write, E1 is write, and E2 is fsync. The valid traces of that program, a trace is like the order that the operations will be in the buffer, the order that they'll hit the disk in. Could be E1, E0, E2, or they could be E1, E2, E0. And what they're saying the model is like a mapping from a program to the allowed set of allowed traces. And then that model has to follow, or that set of allowed traces, each trace has to follow specific rules. And they were talking about them up here. Is that a trace is valid if it respects the synchronization semantic. So if EI comes before EJ in the trace, only if EI comes before EJ in the program, which is tau, and EI is an fsync, a sync, or some file systems have mark and begin. Those are kind of fake in commit. Those are not in POSIX, but they're like, some file systems have that. Or EJ is a sync, or EJ is an fsync on events I, and I is an update on I. Like this, that would mean they have the same file descriptor, because fsync takes a file descriptor. So
Are these tools mandated by POSIX?
I don't think so. Let me see. Where did I go? See, Roman letter T is the total order of the events as they actually occur, but Greek letter tau is the the actual like how the program would, the order that they occur in the program. And these rules, yeah, I was actually unclear where these rules come from. It probably actually, they probably are mandated by POSIX actually. Yeah, because POSIX tells you about sync and fsync. But POSIX doesn't tell you about mark and begin and commit. But some file systems have commit, like especially in parallel, in supercomputer file systems have commit, like I think Lustre. But okay, so it's like a combination of stuff that's in POSIX. And then, yeah, they talk about the different strengths. And I think the one interesting thing is actually characterize what ext4 does, which is kind of neat, in my opinion. Which is that it's like, if I comes before J in the program, when does it also come before J in the trace? That's like the question that they're seeking to answer. And the conditions are when any of the following hold. When one of them is like a set adder on the same file, when one of them is a write on the same file and the same block. That's like kind of an interesting thing. Or where there are updates to the same directory. So, yeah. And there's another paper that might be worth reading if you're interested.
So did that 2009 event and or this paper cause any sort of change in the file system implementations, or is this more of like a win?
I think it more causes change in the applications. I think the applications change how they are because of research like this. Like I forgot it was this paper that said they like actually identified bugs in stuff, and then they told the applications to be better. But yeah, and like I think that in practice you should just use SQLite because they've already told SQLite to debug it. So.
So is the like proper solution to this to just sync the file system before you rename?
Well, I think you should decide if you care about crash consistency. Firefox and Chrome have to, SQLite has to. Git kind of maybe doesn't need to, and like, yeah, I don't know.
Why do you think it would?
Because you can always like go back and like do the operation you're doing again. And you like, it seems like you would not lose data if you encounter a crash during a Git, but you do lose data if you encounter a crash while you're like adding a bookmark or something, or could create corruption. I'm not really sure. Maybe they do have to make sure they're all atomic though. So you have to find out if you need it. If you do need it, you should use SQLite. And if you can't use SQLite, then you have to use fdata-sync, or like you have to like think about it harder. That's what I'd say.
Wait, so it's like SQLite is ensured that like your transaction is SQLite atomic and SQLite transaction is file system atomic?
Okay, let me think. SQLite makes different guarantees depending on the flags you give it. And there's one that is, yeah, like you shouldn't think about it that way. You actually don't know how SQLite talks to the file system, but you know that somehow SQLite gives you an atomic store.
Well, you know, like you should presume that SQLite is just, it works.
Yeah. Okay. Yeah. And when you're talking to SQLite, that is atomic. You know, like maybe SQLite talks to the file system in some super weird non-atomic way. But yeah, it's abstracted. Yeah, and that is time. But if you have more questions, you can let me know.